Last time we did proofs using truth tables. Now I want to introduce logic laws, which show a bunch of really useful logical equivalences that we can use to reduce complex formulas into simpler ones. So last time I introduced the terminology tautology and contradiction. I'm going to define T as a tautology. So this capital T will always mean a formula that outputs ones, and the capital F will always be a formula that always outputs zeros. So the truth table for T essentially looks like 1, 1, 1, 1 all the way down until however many rows there are, and the truth table for the false will always look like 0, 0, 0 all the way down however many rows there are, and 0. Okay, so the first laws I want to introduce are the identity laws. And with truth tables, we can prove these really quickly. So for most of the proofs, you can check logical equivalence using a truth table, which is good practice, but I won't do the truth tables here. I'll just kind of tell you about them and reason through them. So P and true is logically equivalent to P. So P and true, it's going to be true when both P is true and the tautology is true. Well, the tautology is always true, so this just reduces to whenever P is true. P or false, well, this is true when either P is true or F is true, but F is never true, so this is just the same thing as P being true. And these are identity laws because, well, if you give it P, then it outputs P again. Domination laws are a little bit different. So in domination laws, whatever P is doesn't matter. Because if we have P or true, well, true is always true. Therefore, this will output true. P and false, well, false is always false. Therefore, this will output false. Now we can see how the truth and falsity are dominating over our formula. So, given the identity laws and domination laws, let's reduce this P or F and Q or T as far as we can. So let's focus on P or F first. What do we do here? Well, let's use the identity law. P or F will give us P. So now we're left with P and Q or true. And this is identity. So usually we want to write on the side somewhere what rule we did. And I'll just shorten it for ID for identity. Now let's do Q or T. So we'll have P and then what is Q or T? Well, this is the domination law, which means we're going to get true out of it. And this is the domination law. Now we're left with P and T. So what happens now? Well, we have an identity law that says that this is just equal to P. So this is the identity law. So if we have a formula, P or F and Q or T, we can just replace it with P because they're logically equivalent. Similarly, if we have P, we could replace it with any of the ones above because they're all logically equivalent to each other. So those are the first two laws. Now let's do a few more laws. The first one is double negation, which says if we have not P, that's just the same thing as P. Why? Because if P is true, then not P is false, which means that not P must be true. So this is very easy to see with the truth table. If you reverse the values twice, it's like not reversing it at all. The second one is De Morgan's law. In fact, we proved one of these using a truth table last time, and that's if we have not P and Q, that's the same thing as not P or not Q. And if we have not P or Q, that's going to be the same thing as not P and not Q. So a good way to remember this is if you have not and then some stuff on the inside, you distribute the negation sign to the statements, and then you flip the connective. So if we have not P and Q, we give the not to the P and the Q, which is shown here, and then we flip the and to an or. And this will also work for the other case where we have not P or Q. We give it not P, not Q, and we flip the or to an and then we end up with not P and not Q. So let's simplify not P and not Q? Well, the first thing we can do is do De Morgan's law on the entire thing. So we can distribute the negation to not P and not Q. So we'll end up with not P, not Q. And then we'll flip the and to an or, because we're doing De Morgan's. And this is usually shortened as DEM for De Morgan's. Now finally, we have the double negation law. So not P, not Q, we can just change this to P or Q, and this is DN for double negation. So instead of writing not P and not Q, we can just write P or Q. Alright, the most important one out of the four so far that you've seen is definitely De Morgan's law. This is used everywhere in set theory, in propositional logic, and Boolean logic. This is a very important law. So definitely, if you're going to remember one thing from this entire video, remember De Morgan's law. Okay, some more laws. Distributive law and absorption law. Before I give you the distributive law, I want to show you an arithmetic example first. So I have 3 times 1 plus 2. Now, instead of adding 1 plus 2 together, I can multiply these a little bit differently. I can think of this as multiplying 3 times 1 and then adding 3 times 2. So that's another way of looking at 3 times 1 plus 2, as 3 times 1 plus 3 times 2. Now the distributive law looks very similar. If I have P and Q or R, let me just color code this. So let's color code the multiplication as purple, and let's color code the addition as green. So when I take a look at the distributive law here, I am going to do the same thing. So P and Q or R, I can split this into 2 parts. One will be PQ, the other will be PR, and the AND is being distributed to P and Q and P and R, and then the OR is staying in between. Now this looks very similar to the multiplication and addition example below. Similarly, if I do the same thing with the other case, with P or Q and R, it looks exactly the same. So we'll have PQ, PR, and then the ORs will get distributed, and the AND will be in between. So when you think of distributivity, when the ANDs and ORs are flipped, think just like multiplication and addition. Okay, finally, the absorption law. If we have P and P or Q, or P or P and Q, so they flip, but we have P's in both, then these just reduce both to P. And we can see this with the truth table pretty clearly. Of course, P and P or Q is going to be true only when P is true. And P or P and Q, again, we have a P and Q in here, so that'll be true only when P is true. So now that we've done those, let's do an example with not P or F and not Q. First thing I'm going to do is double negation on the not P and the not Q. So I'm going to end up with P or F and Q. And that is going to be double negation twice. Now I'm going to do the P or false. So I'm left with P or, well, P or false, which law is this? Is this domination or identity? Well, this is identity. So this is P or P and Q. And it's identity because, well, P or false is never true, so it's only going to be true whenever P is true. So it spits out P, therefore it's the identity. Now we have P or P and Q. Well, this looks just like an absorption law. So this is P by absorption. Therefore, not P or F and not Q is just the same thing as P. So why would we write such a ridiculous long statement when we can just write P? Okay, we are almost done with these laws. we have some laws that are kind of straightforward that we usually take for granted sometimes. So P and Q, the commutativity law just says that we can flip the order. So instead of P and Q, we can do Q and P. And this is true for or and. So P or Q is logically equivalent to Q or P. Okay, that's commutativity. Associativity says if we have P and Q and R together, then we can just do P and Q first and then do R. And of course, this is also true if we have ORs there instead. But make sure they're both the same thing, otherwise we're dealing with distributivity instead. Inverse laws. P and not P. This is a contradiction. This is false. We've proved this in the last video. P or not P. This is true. This is a tautology. Once again, we proved it in the last video. The only one that might be a little bit confusing at first is the conditional law, which is that P arrow Q is the same thing as not P or Q. So if we just take a look at the truth table really quick for this one. PQ, P arrow Q. So this would be 1, 1, 1. So I'm just going to fill out the truth table really quick here. So P arrow Q. It is true when P is false. So it's true in these two conditions when P is false, or when Q is true in these conditions. So not P or Q captures every single environment where P arrow Q is true. So that's the conditional law. This is why P arrow Q is equivalent to not P or Q. In fact, we could have proven it with a truth table more clearly actually to show that not P or Q is the same thing. So why don't I do that right now actually? So if we have P1100, then not P is going to be 0011, which means not P or Q. Well, Q is true in the first row, neither are true in the second row, in the third row, not P is true, and in the fourth row, not P is true, so we have 1011, which is also output the same thing. So they're logically equivalent. Now, as an exercise, let's show that not P and Q is logically equivalent to not P and Q. So the first thing we'll always do is we'll just write out the first step as an assumption. And then we'll work step by step to get something that we can work with. So the first thing I see here is I see a not, and then I see a P and a Q together. Whenever I see a not outside of brackets, I want to De Morgan's them together. So let's use De Morgan's law first. And we'll end up with not P, not Q, and then we flip the and to an or. So this is not P or not Q, and then the and Q is left the same, and this is De Morgan's. Okay, so now I have not P or not Q and Q. So I see that these ors and ands are different, so we can use distributivity. So let's color code this once again, just to see distributivity. So what this will look like is we'll have Q not P together, we'll have Q not Q together, the ands will be distributed in, and the or will remain in between. So it's like grabbing Q and not Q, and then Q and not P together. Okay, and that was distributivity. Now what do we have? Well, Q and not P, we can't do anything with that, but Q and not Q, well, what is Q and not Q? That is a contradiction, that is false, and that was the inverse law. So now we're left with Q and not P, or false. Now what happens if I have anything or false? Well, anything or false, that's just left with the anything I had before, because that is an identity law. And we just saw this earlier too. This is identity. So we're left with Q and not P, which then, using commutativity, we can flip the order around to get not P and Q, and that's by commutativity. Therefore, not P and Q is logically equivalent to not P and Q. So that's it for logic laws. If you have any questions, feel free to ask, and I'll do my best to respond to them.